Hey guys, how's it going? So, ever since I've taken analysis courses in my undergraduate studies, especially complex analysis and I'm doing partial differential equations right now. Ever since I've taken courses that requires proofs, I've been inclined to prove like just about everything that I've been that I've done or taken for granted in the past that I didn't have to prove, like, the sine law, cosine law. And I want to be able to prove things and not just take things for granted. So we're going to be doing two proofs today. One of them is I'm going to prove the derivative of the power rule. And the second one is I'm going to derive Euler's formula, which is e to the I theta is cos theta plus I sine theta. So let's go with, so first of all, let's start off with the power rule. F of x is equal to xn. And you already know that the derivative of this is, and you already know that the derivative of this is nxn minus 1. So yeah, xn. So let's find the derivative. There's two ways to find the derivative. The first one is I'm just going to go by the definition of the derivative. And the second one, I guess you'll have to see. So as you know, it's f of x plus h minus f of x over h. And that is equal to, okay, so f of x plus h, f of x is x to the power of n. So f of x plus h is x plus h to the power of n minus xn all over h. Shit, I forgot to include the lim h tends to 0 thing. So lim h tends to 0, x plus h. And thank God I'm not using doing this without the pen. Otherwise, that mistake would have cost me an extra 3 minutes. Okay, so the binomial theorem, and we're going to use that. But before I do that, I'm going to show it here. So x plus, so I'm just going to show the general case. Okay, so x plus y to the power of n is equal to, if I recall correctly, I think it was okay, so I think it was n0, yeah, or n equals something, n equals 0, let me think, x to the n, no, x to the k, yeah, x to the k, not n, y to the power of n minus k. Oh, no, it was k sub 0. Okay, I remember now. Yeah, it was k equals 0 all the way to n, and then n factorial k. I'm remembering now. This is the binomial theorem. Yeah. Okay, so we're going to apply that here and say that, okay, so that's equal to lim h tends to 0, factorial k equals 0, n, okay, so then nk x to the power of k, y, h, because since it's x plus h, h to the power of n minus k minus x to the power of n all over h. All right, and then this is equal to, let's just expand that binomial thing out. Lim as h tends to 0. Okay, so then, yeah, so when k is 0, so then that's n factorial 0, x, shoot. I am getting way ahead of myself today. Okay, so I think it was wait, x to the n minus k, y to the power of k. Yeah, okay, that makes more sense to me. I am so sorry, guys. I hate it when I make mistakes. X to the n minus k, h to the power of k. Okay, and now, so then when k is 0, that's just x to the power of n. And then h to the, k is 0 right now, so h to the power of 0 is just 1 plus n 1 x to the n minus 1 h, because h to the power of 1 is just h, plus so n2 x to the n minus 2 h squared. Let's do one more, plus n factorial 3 x to the n minus 3 h cubed, plus so on and so forth. And then, yeah, just means for the rest of them, plus n, this is the last term in the binomial expansion, x to the 0 h n minus x n all over h. Okay, and then that is equal to, okay, so let's figure out some of these terms. N factorial 0 is just 1, so okay, let's just, I didn't forget this time. N factorial 0 is just 1, so that's just x to the power of n, plus, so n factorial of 1 is n factorial over 1. That's just n minus 1, I think. N1. Yeah. Okay. N minus 1. Wait, hang on. Let me think. N1 is equal to N1 and 1. No, it's just N. So yeah, that is just equal to N x n minus 1 times h. Let's erase this. And then plus, okay, so n factorial 2 is n times n minus 1. I know this is true, guys. You don't have to worry about me making a mistake now. X n minus 2 h squared, plus n minus 1, n minus 2, that's n to the 3 factorial, x n minus 3 h3 plus dot 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 plus n to the, that's 1, that's h to the power of n minus x n all over h. Okay, we can first of all, xn here subtracts, cancels out with xn there. So then that we can do this. So lim, because the xn's cancel out, every term, preceding term here in the numerator has a greatest common factor of h. So we could factor that out actually. So I'm just gonna go divide that. So brackets here. So h divided by h is just 1. So nx n minus 1 plus n minus 1 x n minus 2 times h plus n minus 1, n minus 2, x, n minus 3, h squared, because h cubed over h is h squared, plus h to the power dot 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 plus h to the power of n minus 1. And I can see, I hope you can see the pattern here of why I didn't consider all the middle terms of the binomial expansion for x plus h to the power of n. It's because they all contain a multiple of h, and h tends to 0. So then all these terms that have an h, a factor of h, would all equal 0. It's like this is equal to 0, h squared is equal to 0, h to the power of n minus 1 is equal to 0. So they all equal 0 except the n times x minus n minus 1 term. So f prime x is thus proven to be nx n minus 1. You've already seen this in, yeah. If you guys don't like proofs, you can just go ahead and use this formula for the derivative. But I'm warning you, if you just go ahead and take something everyone says, you will cry about it later if you take upper level maths. Okay, like I always give you guys the solution, but I highly encourage you to find the reasoning behind things. The second way to find the proof is by using the product rule and doing this. So f of x is x to the power of n, which is x times x to the power of n minus 1, which makes sense, right? Okay. And we just treat it x and x to the power of n minus 1 as two products, and then just apply the product rule. So f prime x is just equal to, so take the derivative of x as 1. So that's x to the power of n minus 1 plus x. Now let's take the derivative of x to the power of n minus 1, and using the power rule, that's n minus 1 x n minus 2. Okay, and then that is equal to x, let's simplify a bit, plus n minus 1 times x to the, so x to the power of 1 times x to the power of n minus 2 is x to the power of n minus 1 in the second term. And that is equal to, you can factor out an x to the n plus minus 1 on both terms here. So x n minus 1. After you factor out an x to the n minus 1 here, you're just left with 1. And then factoring that out, you get plus n minus 1, which just leaves you with n, so which is equal to nx n minus 1. See, we once again proved the power rule. So that is the power rule. Yeah, just the proof of it. Okay, let's now prove Euler's formula. So let's prove that e to the I theta is cos theta plus I sine theta. How do you do that? That's actually a very good question. We're going to, first of all, write e to the I theta. And I'm going to do something on the side here. I'll erase this. As you may have learned from your Calculus 2 class, e to the power of x is equal to, from n equals 0 to infinity, x to the power of n over n factorial. If you guys don't know the proof of this, go to my video where I talk about the Maclaurin series, and I perfectly explain it there. All right, so when you do this, you can just use substitution, and you can just substitute x is equal to I theta into this series expansion. So then e to the I theta, applying this formula, so then remember x is equal to I theta in this equation. So n is equal to 0 to infinity of I theta to the n over n factorial. I'm gonna erase this now. I'm gonna give you guys 3 seconds to look at it. 1, 2, 3. Okay, now I'm gonna erase this. You can always pause the video if you like and just capture that formula. Okay, so there we go. Now we can expand this. So, which is equal to n equals 0 to infinity, I to the power of n, theta to the power of n over n factorial. And that is equal to, okay, so let's just go step by step until we see a pattern. I'm going to go until n equals 5. Okay, so when n equals 0, I to the power of 0 is 1. Theta to the power of 0, that's just 1. And 0 factorial is 1, so that's 1. Okay, plus I to the power of 1 is I. Theta to the power of 1 is theta over 1 factorial. You know, yeah, let's do a 1 factorial. You'll see why I'm writing it like this later. Okay, minus, the reason I do a minus is because I squared is equal to -1, and then theta squared all over 2 factorial. Because, yeah, n factorial is 2 factorial. Minus I, because I cubed is I squared times I, which is -I. So -I, theta cubed over 3 factorial, plus I to the power of 4. Now n is equal to 4, so I to the power of 4 is 1. Theta 4, theta to the power of 4 over 4 factorial. Let's do one more. Plus I to the power of 5 is just I. Theta to the 5 over 5 factorial. And let's just do plus ... Okay, now we have it written like this. Let's separate it out into its real and imaginary components. Let's separate this term into its real and imaginary components, okay? So for the real part, we have, I'm just going to write this in brackets because I want to distinguish them very carefully. 1 minus theta squared over 2. Factorial. Okay. Plus theta squared over 4 factorial minus ... plus I times, you could have done one more term, but I know the formula for this already. So I'm just going to stop here. You could have said, wait, that's supposed to be a 4. Sorry about that. Okay. I could have like said plus minus theta 6 over 6 factorial, but I know the formula already. So I times, okay, so then theta over 1 factorial minus theta cubed over 3 factorial plus theta 5 over 5 factorial minus yada, 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 like that. And you should be able to immediately derive a series out of both these components. Let's start with the real first. So it's from n equals 0 to infinity, because it spans on to infinity. And notice that at the power, it's at every even power, an even factorial does such a term exists for the even component. And it alternates from positive to negative to positive to negative to positive and so on and so forth. So since it alternates from positive to negative per term, we write -1 to the power of n. And we do theta to the power of 2n since the powers are even. And since the factorials are also even, we do 2n factorial, like that. Now, plus I, because now we're considering the imaginary component part now, n equals 0 to infinity. Like the even component, the odd components also alternate between positive and negative. So the first thing I'm going to do before anything else is -1 to the power of n. Okay, and then I also noticed that it's every odd power and odd factorial where such a term exists for the imaginary function component. So basically that's theta to the 2n plus 1 and over 2n plus 1 factorial. All right, and if you may remember, if you took the time to memorize or you probably did this before with sine and cosine, you should be able to recognize that these are the series for cosine and sine respectively. So then this is cos theta plus I sine theta. And we are done. Okay, so that's all for this video. Thank you very much for watching. I'd love to stay, but for now, I gotta jump. I'll see you guys on the other side of the bridge. Catch you next time.